Another method of mathematical proof is based off of the principle of mathematical induction. Okay, this is a basic axiom of the natural numbers, and such we assume it without proof. However, it kind of is how we all understand the natural numbers to be, so it's largely accepted without any problems. Okay. Now, I call it the domino principle. Okay. Because if you have ever set up a whole bunch of dominoes and then flicked over the first one and stood back and watched them fall, this is what is happening here. Okay, so to make that trick work, when you set up the dominoes, you must make sure that every domino is close enough to the one before it that it will get knocked over by that one. Okay, that's essentially this second step. Then you must actually flick over the first one yourself. That's this step. And then you stand back and watch them all fall down. Okay. It somewhat feels like magic. I'm going to just tell you that. Okay. It is also absolutely critical to do the base case, which is step 1. Okay. Even though that is usually trivial to prove, you have to do it. If you never flick over the first domino, no dominoes ever fall. Okay. So, what is it we do? Okay. If we have some statement that is trying to be true about natural numbers, okay, we prove the first instance ourselves. Usually that's n equals 1, okay, but it could just as easily be n equals 5, or n equals 17, or n equals 1032, okay, but it must start somewhere. Then we assume what is called the induction hypothesis. That is, that I assume it is true for some fixed integer natural number, and prove that would imply it is true for the next one. Okay. And then I say, by induction, it's always true. Okay. All right. So let us illustrate this. Okay. I'm going to start with what is often called Gauss's formula. Okay. For n in the natural numbers, the sum of the first n natural numbers is n times n plus 1 over 2. Okay. So what makes me think to prove this by induction is the fact that it is a statement about natural numbers in the first place. Okay. All right. So we proceed by induction on n. Okay. All right. So my first case, well, I'm assuming it's true for all natural numbers, so the smallest one is 1. Okay, so is this statement true for n equals 1? Well, the left-hand side of the statement says add up all the numbers from 1 to 1. That's just 1. The right-hand side of the statement says take 1 times 1 plus 1 all over 2 and see what this is, and this in fact does equal 1, so I'm good. I did tell you the base case is often trivial. Okay. So, we then assume this statement is true for a fixed n. And we will try to prove it's true for n plus 1. Okay. By the way, that means that down here somewhere, I want a statement that is add up the numbers from n1 to n plus 1. And get the similar statement if n was replaced with n plus 1. So this is what I'm looking for here. You may notice that I'm going to basically work this proof from both sides. Okay. This means, if I clean up that right-hand side, that what I'm really looking for is this. Okay. All right. So let's go back up here. 1 plus 2 plus 3 plus n plus 1. Well, if I just take the first n numbers by my induction hypothesis, I know what that equals. But then, of course, I still have to add n plus 1. Okay. Now, since I'm attempting to get a statement with only one fraction, the obvious implication is I should add the fractions. And, of course, in order to add fractions, I need to force a common denominator. Okay. This gives me n squared plus n plus 2n plus 2 all over 2. Okay. Or n squared plus 3n plus 2 all over 2. which lo and behold factors as n plus 1, n plus 2, exactly as I desired. Okay, so I say, hence, by induction, the statement is true for all n in the natural numbers. Okay. All right. I'm going to do another example, and in so doing, I'm going to prove a very useful fact. Okay. This is called Demov's theorem. Okay. It says if n is a natural number and theta is a real number, then cosine of theta plus I sine of theta to the n equals the cosine of n theta plus I sine of n theta. Okay. And of course, I here is in fact the square root of -1, and that fact will be important later on in the proof. Okay. All right. We proceed by induction on n. And it has to be on n instead of theta because induction only works with natural numbers, not with real numbers. Okay. So, n equals 1. Well, if I plug in 1 for all the n's, I get cosine theta plus I sine theta to the 1 equals cosine of theta plus I sine of theta, which is completely trivially true. Okay. So now we will assume the statement for n and attempt to derive it for n plus 1. Okay, so starting with the left-hand side, for n plus 1. This is, according to rules of exponents, this is cosine theta plus I sine theta to the n times cosine theta plus I sine theta. Okay. The first one, by the induction hypothesis, equals cosine of n theta plus I sine of n theta. All right. Now that I no longer have exponents in the way, I will simply FOIL. Okay. I get cosine n theta cosine theta plus I cosine n theta sine theta plus I sine n theta cosine theta plus I squared sine n theta sine theta. Okay. And I appear to have extra parentheses randomly hanging around. Okay, now I'm going to group the real portions and the imaginary portions, also of course noting that I squared is really -1. Okay, so the real part is cosine n theta cosine theta minus sine n theta sine theta plus I times cosine n theta sine theta plus sine n theta cosine theta. All right, now we're going to use a fact from trigonometry, okay, known as the sum and difference identities. Okay, by the sum and difference identities, feel free to look those up if you can't remember them. This first bracket is exactly equal to cosine of n plus 1 theta, being n theta plus theta. And the second bracket is exactly equal to sine of n plus 1 times theta, once again being n theta plus theta, which is exactly the statement I wanted. Okay. Thus the statement is true for all n. So this is a typical example of an induction proof, okay, in that the induction hypothesis, we deal with most of the work, and then we just have to somehow include the one extra piece.